In this video, we're going to be talking about thermal resistance circuits, and a way to end this is going to be talking about ways you can save money by switching to Geico. I'm sorry, by switching to double paned glass windows in your home. And so to get started, we're going to look at thermal resistance. Specifically, we're going to be looking at how heat flows through a system via conduction. And so if we recall something from electrical physics, or whatever they call it, V equals IR was Ohm's law. It tells us that we've got some potential difference is equal to the current times the resistance in a particular circuit, for instance. And so just like with electrical circuits, we can look at thermal circuits in a very similar way. And so if we think of voltage, this potential difference, as a difference in temperatures between two places or two mediums, we can do that. So I've drawn this little diagram off to the left here of a bunch of different mediums in series. So I've sandwiched three things together. And on one face of this, it will have a temperature. I'll use some color here. I'll call it T1. And then on the other side of this thing, it'll have a temperature T2. And so what voltage really is, in this case, we can think of as being just T1 minus T2. So just like you had that potential difference with electricity, we have a potential difference with temperature. And in terms of current, we'll write this like a clean eye, this current guy is really your heat flow. Because just like with electricity, we care about how many electrons are flowing through. With thermal stuff, we care about how much energy is flowing through our system. So I is really just Q, which is equal to heat flow. So instead of looking at electrons, we're looking at energy. And then finally, we've got this resistance thing. And well, resistance is just resistance. Same kind of resistance we're used to with electric circuits. And so how can we rearrange this equation so that we can begin to model the way in which thermal energy moves through a system via conduction? So the way you do that is just by dividing some terms around and doing some algebra. And so what you ultimately arrive at, and I'll try to use nice colors here, is the following. So we've got Q, the heat flux in our system, is equivalent to T1 minus T2 quantity divided by R. And so if we were looking at a single resistor, that would be it. It would be a pretty simple process, right? Because we'd only have one resistance, and that would be R. And specifically what we want, though, is R total. So just like what we did with electrical circuits, where we tried to figure out ways we could combine resistors together into like a big resistor, and how to look at resistors in series and combine those into a big resistor that we could then call R total, we're going to do the same exact thing here, but with thermal resistance. And so in my little example here, I've got three separate mediums, and the property of each one of these materials gives it a different thermal conductivity, which is that K term. So K1, K2, K3. And so the key thing to make note of here is that the resistance, I'll call it I, so of any one of these three things, is really just equal to the length of that thing, so L sub I, divided by K sub I, whatever that thing's thermal resistance is, times that thing's area, so A sub I. And I'm going to assume that all my things here have the same area, so I can really just simplify this a little bit and take off that I term, and I'll try to write that I a little bit more cleanly. But that is what we really care about here. So this R sub I is how we're going to determine the individual resistance for each one of the mediums present in our thermal circuit right here. So with that out of the way, we can then go about determining what is R total. And so just like with electrical circuits, again, there's a beautiful analogy here. If we have stuff in series, what do? You really just add these three things together. And so a fun way to just think about this is it's literally just this. You got 1, 2, 3 resistors. I apologize, my handwriting is poor, but you get the idea. We've just got three separate resistors in series right here. And so because we know what the individual resistance is, we can sum all of these terms together to arrive at what our total resistance will be in this particular thermal circuit. And so by doing that, what we really arrive at here is the following. So what is R1? So R1 here is really just equal to the length of 1 divided by k sub 1 times its area. And then we just do this for the other guys. So ab nauseum, R2 is equal to L2 over K2 times A. And then R3 was really equal to L3 over K3 times A. And all we do is we add up these guys. So it's pretty straightforward algebra by this point. And so what we arrive at, we'd have L1 over K1 plus L2 over K2 plus L3 over K3 quantity times 1 over area is equal to R total for this system. And something I want to make note of here, just in terms of hopefully there's some sanity checks we can have along this way, is to think about this intuitively. So if I increased the length of a particular material, that's going to be more stuff that energy is going to have to flow through. So intuitively, this should make some sense, right? Because if you had to flow through more stuff, that stuff's going to give you more resistance because you have to do more work to get through it. And same thing goes for this K term, this thermal conductivity of our particular material. If we have something that's very thermally conductive, what that means is it's going to have a very large value. Consequently, it's going to have that inverse effect on its resistance. So if something's really conductive, it's a poor resistor, and therefore we're going to have a very high R total resistance. And so hopefully this makes sense. And if we applied some numbers to this thing, we could very quickly arrive at what the total heat flow through a particular system is if we know all these characteristics. So that is how we model this process, and so that's how we handle things in series. Now what I'm going to do, though, is we're going to look at things in parallel. So if I stacked some Legos on top of each other and we applied this same thing, what would it look like? So we've got T1 on the left here. We're going to have, T2 on the right. And each one of these materials, I will again, just for the sake of simplicity, say that they all have the same area, like that. How do we handle this system? Well, it's really just this, where we've got 3 resistors in parallel, and they're contributing to this total resistance. So now we've got R1, R2, R3. Try to write cleanly. And so our goal here is to figure out what is Q. So what is that energy flow through the system? And so the way we do that, and how do you calculate what is R total when you've got resistors in parallel, is you do the following. So 1 over R tot equals 1 over R1 plus 1 over R2 plus 1 over R3. I apologize, that's off the page a little bit, but hopefully you guys get the point. So again, very simple process, and we just look to our definition of what is R sub I, and we know that R sub I will be equal to L sub I divided by K sub I times the area. And so we can just do that for this too. So 1 over R total is really equal to, and we're going to do the inverse now of R. So that means I'm going to have K1 times area. K1 times the area divided by the length of that. And so in this case, the length, again, would be in this one-dimensional x-axis thing. So that's L sub I. And what I'm going to note here is how, we can say in parallel, these things will all have the same length too. So it becomes we can simplify that algebra too. And so we're just going to continue performing this process. So L sub I is going to be L for all the 3 mediums that we have. And so we're just going to keep going. So we've got K2 times its area divided by L times A. And I'm just going to keep assuming that they've all got the same areas. Obviously, don't do this on a test unless you were explicitly told you could do that. But yeah, and so that's what this thing is. And then in our particular example, 1 over R tot in this parallel circuit for this specific situation is going to be, we can pull out area over length for all these terms, and then we'd have K1 plus K2 plus K3. And so that is how we can calculate this. And then R total is just the inverse of that. So R tot for our parallel resistor or thermal resistor circuit is going to be L over A, and then times the inverse of K1 plus K2 plus K3 inverse, just like that. And I apologize if this is hard to read, but I'll try to make it clear. So this guy is how we would calculate R total in this particular circuit. And then we would just fall back on that generic equation that we had up top, which tells us that Q, the energy flow, is really equal to the temperature difference between these two mediums divided by that R total. So delta T over R tot, and there's R tot. And so that is going to wrap things up for an introduction to how we look at stuff in parallel versus in series for thermal resistance circuits. And what I'm going to do next is talk about how a double pane window will save us a lot of money on our energy bill every year because of the increase in resistance to those thermal conduction losses that we get from upgrading our windows. So stay tuned for that. Thank you all for watching. Hope your mother's doing well. I'll talk to you guys next time.